We're going to take a look at some ways that using trig substitutions will allow us to find antiderivatives for functions that we haven't been able to do that for. To motivate why we might need to do this, let's consider the graph of y equals x squared. And imagine we want to calculate the length of that curve between x equals 1 and x equals 2. This seems like a pretty straightforward problem. We know that calculus tells us that that length is equal to the integral from 1 to 2 of the square root of 1 plus f prime of x squared, which is the square root of 1 plus 2x squared, or the square root of 1 plus 4 times x squared dx. That is, at this point in time, not an integral that we have a technique to evaluate. However, we'll come back to this problem at the end and see that now we'll have a way to solve it. We're going to look at 3 different substitutions we may wish to make. The first will involve integrals involving things of the form a squared minus b squared x squared. The next group will look at integrals involving b squared x squared minus a squared. And then the last group will look at integrals involving a squared plus b squared x squared. When our integral involves something of the form a squared minus b squared times x squared, we're going to make a trig substitution that will hopefully then introduce an integrand that we already know an antiderivative for. So let's look at a right triangle. Here we have an angle theta. If we put bx on the opposite side and a on the hypotenuse of that triangle, then the missing third side would be the square root of a squared minus b squared x squared. We can then look at the triangle and see that the sine of theta is going to be equal to opposite over hypotenuse, which is bx over a. That tells us then that a times sine theta is equal to b times x. That then gives us that a squared minus b squared x squared is equal to a squared minus a squared sine squared theta. We can use some Pythagorean identities now. By factoring out the a squared, we get 1 minus sine squared theta, which becomes a squared times cosine squared of theta. Let's look at an example to see how this is useful to us. We'll take a look at the antiderivative of the square root of 49 minus x squared dx. So in this case, our a value is 7 and our b value is 1. We're going to write x equals 7 times the sine of theta, which will give us that dx is 7 cosine theta d theta. Plugging that in, we get the square root of 49 minus 49 sine squared of theta, all times 7 cosine theta d theta. We can factor out of 49, so now we have the square root of 49 times 1 minus sine squared of theta, still times 7 cosine theta d theta. We can break apart the square roots now, so we get 7 times the square root of 1 minus sine squared theta times 7 cosine theta d theta. We'll combine the two 7s and bring them to the outside to get 49 now times the antiderivative of the square root of cosine squared theta using a Pythagorean identity times cosine theta d theta. Well, that becomes 49 times the antiderivative of cosine squared theta d theta once we take our square root. We'll use a half angle formula now. So we're going to rewrite cosine squared theta as 1 plus cosine 2 theta over 2. Bring in the 2 to the outside. Now we anti-differentiate. So we get 49 over 2 times theta plus 1/2 the sine of 2 theta. Of course, we'll add on our constant. We're going to rewrite sine of 2 theta as 2 sine theta cosine theta. But the 2 and the 1/2 cancel, so we just get 49 over 2 times theta plus sine theta cosine theta plus c. Now, our original problem was not in terms of theta, it was in terms of x, so we need to get back to x's. So we'll notice that x is equal to 7 sine theta tells us that theta must be the inverse sine of x over 7. If we think about this in terms of a triangle, we already know by our original substitution that sine of theta is x over 7, but we still need to know cosine theta. So if we draw a triangle with the opposite and hypotenuse labeled as x and 7, then the adjacent side must be the square root of 49 minus x squared, which makes the cosine of theta the square root of 49 minus x squared over 7. So we can now plug all those values in, and we get 49 over 2 times the quantity inverse sine of x over 7 for theta. And then we're going to do sine theta times cosine theta, so that's x over 7 times the square root of 49 minus x squared over 7. Still plus our constant. And if we distribute the 49 halves, we get 49 halves inverse sine of x over 7. And then we get x times the square root of 49 minus x squared all over 2, because the 49 cancels with the 2 7s in the denominator. Let's try another now that involves a definite integral. So we're going to take a look at the definite integral from 0 to 3 halves of the function 1 over 9 minus x squared all to the 3 halves power dx. If we let a be 3 and b be 1, then we can see that the bottom is in the form a squared minus b squared x squared, which means we can proceed with similar substitution. Letting x equal a sine theta gives us that x is equal to 3 sine theta. Dx must then be 3 cosine theta d theta. So now we have the integral of 3 cosine theta all over 9 minus 9 sine squared of theta to the 3 halves power times d theta. We need to consider our new limit. So when x is 0, that means that 0 is equal to 3 sine theta, which means that the sine of theta must be 0. So theta must be equal to 0. When x is 3 halves, we get 3 halves is equal to 3 sine theta. Dividing both sides by 3, we'll get 1 half equals the sine of theta. And so then we know that theta must be equal to pi over 6. So now we have the integral from 0 to pi over 6 of 3 cosine theta over 9 minus 9 sine squared theta to the 3 halves. So when we can simplify the bottom, factoring out a 9, we have 9 to the 3 halves times 1 minus sine squared of theta to the 3 halves power d theta. We'll use our trig identity again. So we get the integral from 0 to pi over 6 of 3 cosine theta over 27, that's 9 to the 3 halves, times cosine squared of theta to the 3 halves. We can factor out the 3 and 27, so we get 1/9 times the integral from 0 to pi over 6 of cosine theta over cosine cubed of theta. When we multiply the squared exponent times the 3 half power, we get cosine cubed. So now we have 1/9 times the integral from 0 to pi over 6 of 1 over cosine squared theta d theta. But 1 over cosine squared is the same as secant squared. So now we have the integral from 0 to pi over 6 of secant squared theta d theta. And we know that the antiderivative of secant squared is tangent. So we have 1/9 the tangent of theta from 0 to pi over 6. And since we switched our limits, we don't have to go back to x. So we get 1/9 times the tangent of pi over 6 minus the tangent of 0, which is 1/9 times 1 over square root of 3. We can rationalize the denominator and rewrite that as the square root of 3 over 27. We'll move some things around now and examine integrals that involve b squared x squared minus a squared. We're going to use triangles again to motivate the substitution that we need to make. We'll do things a little bit differently. This time I'm going to label the adjacent side to my angle theta as a and the hypotenuse as bx, making the opposite side b squared x squared minus a squared, all under a square root. When we look at this then, we can see that the secant of theta, which is 1 over cosine, is going to be hypotenuse over adjacent. So we get b times x over a. Multiplying that out, we get a over b times the secant of theta is equal to x. So then b squared x squared minus a squared becomes a squared secant squared theta, the b's canceling out, minus a squared. Factoring out an a squared, we get secant squared theta minus 1, which we know is equal to tangent squared. So our expression on the opposite side is equal to a squared tangent squared of theta. We'll try an example now. Let's take a look at the antiderivative of the square root of x squared minus 25 all over x dx. We can see in that square root that our b squared x squared is the x squared term, so b is 1, and our a is 25, so we can let x be equal to 5 secant theta. That then tells us that dx is 5 secant theta tangent theta. We then know also that x squared minus 25 must be equal to 5 squared secant squared theta, which is 25 secant squared theta, minus 25. And if we factor out a 25 and use a trig identity, we know that that's equal to 25 times the tangent squared of theta. So now we can make some replacements. We have the antiderivative of the square root of 25 tangent squared theta all over 5 secant theta. And then replacing dx, we get 5 secant theta tangent theta d theta. We'll take the square root of our numerator to get 5 tangent theta over 5 secant theta times 5 secant theta tangent theta d theta. We can tidy this up by canceling some terms. We've got a 5 secant theta in the numerator and the denominator, so we'll cancel those out. And when we rewrite this, it becomes the antiderivative of 5 tangent squared theta d theta. We know an antiderivative for secant squared, so we'll use our Pythagorean identity one more time and rewrite tangent squared as secant squared theta minus 1. So now anti-differentiating that, we get 5 tangent theta minus 5 theta plus our constant. Once again, we need to rewrite things in terms of x, not theta. So we'll look back at our triangle. We'll recall in that triangle that we're using x is equal to 5 secant theta. So x is going to go on our hypotenuse. 5 will go on our adjacent side, since secant is hypotenuse over adjacent. And that makes the opposite side the square root of x squared minus 25. So now we know that the tangent of theta is opposite over adjacent, so that's x squared minus 25 over 5. We also know that theta must be the inverse secant of x over 5. So now we'll plug in for theta and we get that our final answer is the square root of x squared minus 25 minus 5 times the inverse secant of x over 5 plus c. Just like with the previous one, we're now going to take a look at a definite integral. So let's examine the integral from 4 root 2 to 8 of dx over the square root of x squared minus 16. We can see that a is 4 and b is 1. So we're going to let x equal 4 times the secant of theta, making dx 4 secant theta tangent theta d theta. Squaring x gives us 16 secant squared theta, which means that x squared minus 16 is 16 secant squared theta minus 16, which becomes 16 times the tangent squared of theta. We'll need to momentarily change our limits, but for now we'll rewrite this as the antiderivative of 4 secant theta tangent theta over 4 tangent theta times d theta. Notice we took the square root of 16 tangent squared for the bottom. If x is equal to 4 root 2, then that tells us that 4 root 2 is equal to 4 times the secant of theta. That gives us the square root of 2 equals the secant of theta, which means that theta must be equal to pi over 4. If we let x be 8, then we know that 8 is equal to 4 secant theta. So 2 is equal to secant theta, which means that theta must be pi over 3. So now we have the definite integral from pi over 4 to pi over 3 of 4 secant theta tangent theta over 4 tangent theta d theta. We can do some cancellation. The 4's will cancel, the tangents will cancel. And so we end up with that. Our integrand is now secant theta d theta. This is one we worked out previously. That is going to be the natural log of the absolute value of secant theta plus tangent of theta. And we're going to evaluate that from pi over 4 to pi over 3. Notice because we're doing a definite integral and we already changed our limits of integration, we do not have to switch back to x's. So we get the natural log of the absolute value of the secant of pi over 3 plus the tangent of pi over 3 minus the natural log of the absolute value of the secant of pi over 4 plus the tangent of pi over 4. So that gives us the natural log of the absolute value of 2 plus root 3 minus the natural log of the absolute value of root 2 plus 1. And if we're feeling particularly fancy, we can combine that into a single logarithm. We get the natural log of the absolute value of 2 plus root 3 over the square root of 2 plus 1. Those are positive numbers, so we can actually remove the natural or the absolute value if we so desire. Our last substitution is going to work for integrals that involve things of the form a squared plus b squared x squared. We'll once again look to right triangles to motivate the correct substitution that will help us out in these cases. Since we have a plus a squared plus b squared x squared, we can assume that the a squared plus b squared x squared has to be the longest side of our triangle, which means that our other two sides must be a and bx accordingly. Looking at this triangle then, we can see that the tangent of theta must be equal to bx over a, opposite over adjacent. That gives us then that x is equal to a over b times the tangent of theta, which means that a squared plus b squared x squared is going to equal a squared plus a squared tangent squared theta. We'll rely again on our trig identities, the Pythagorean identities in particular. Factoring out an a squared, we get 1 plus tangent squared left over, which we know is equal to secant squared. So here we have a squared secant squared theta for our hypotenuse. We'll take a look at an example to see how this will work. We're going to examine the antiderivative of x squared all over 16 plus x squared all squared with respect to x. So we'll let x be 4 tangent theta, noticing that our a is 4 and our b is 1 in this case. Then that gives us that dx is equal to 4 times the secant squared of theta, d theta. And we know that x squared is equal to 16 tangent squared theta. Which means that x squared plus 16 is equal to 16 times the secant squared of theta. Rewriting our integrand, we're going to see that this is equal to the antiderivative of 16 tangent squared theta all over 16 secant squared theta, quantity squared, the entire denominators being squared, and then we have 4 secant squared theta d theta replacing dx. We'll bring the 16 and the 4 out to the front to get 64 times the tangent squared of theta over the secant squared of theta. Then we have 16 squared in the denominator and secant to the 4th when we square secant squared. 64 over 16 squared simplifies to 1/4. So now we have 1/4 times the integral of tangent squared theta secant squared theta when we cancel the secant squared and the secant to the 4th. We're going to use some trig substitutions to simplify this a little bit. Tangent squared is equal to sine squared over cosine squared, and secant squared is 1 over cosine. Since we're dividing by it, we can multiply by its reciprocal, and we see now that our integrand actually simplifies to be sine squared of theta d theta. We know that to do an even power of sine, we're going to use a power reducing identity, so we're going to rewrite that as 1 minus cosine of 2 theta over 2, but we'll bring the 2 out front, making the fraction 1/8. And now we anti-differentiate, so we get 1/8 times theta minus 1/2 the sine of 2 theta. And of course we need our plus c. Our job is now to replace theta, but first we'll rewrite sine of 2 theta as 2 sine theta cosine theta, but the 2 and the 1/2 cancel. So now we're going to look for replacements for sine of theta and cosine of theta, along with theta itself. So we go back to our triangle. We know that x was equal to 4 tangent theta, which means that x over 4 is the tangent of theta. So since tangent is opposite over adjacent, we'll put x on the opposite side and 4 on the adjacent side. That is going to give us that theta is equal to the inverse tangent of x over 4. We also know that the hypotenuse of our triangle, by the Pythagorean theorem, has to be 16 plus x squared, all under a square root. So we can say that the sine of theta is opposite over hypotenuse, so that's x over the square root of 16 plus x squared. And the cosine of theta is going to be adjacent over hypotenuse, which will be 4 over the square root of 16 plus x squared. So plugging in now, we have 1/8 times theta is equal to the inverse tangent of x over 4. And then sine theta times cosine theta will give us 4x times 16 plus x squared. The square roots, when we multiply them together, they go away. And so we have 1/8 the inverse tangent of x over 4 minus 2x, canceling our 4 and our 8, over 16 plus x squared, plus a constant c. We'll do a definite integral now using this method of substitution. So let's look at the integral from 0 to 3 of x squared over x squared plus 9 dx. Since our a value is 3, we're going to let x be equal to 3 times the tangent of theta. That gives us x squared equals 9 tangent squared of theta. So x squared plus 9 must be 9 times the tangent squared of theta plus 9, which we can rewrite as 9 times the secant squared of theta, using tangent squared of theta plus 1 equals secant squared. Dx is going to be 3 secant squared theta d theta. So we have now the integral of 9 tangent squared theta times 3 secant squared theta, all over 9 secant squared theta d theta. We're going to change our limits, so we get, when x is 0, that 3 times the tangent of theta is 0, which means the tangent of theta is 0, which means theta must be 0 degrees, or 0 radians. If x is 3, we get 3 tangent theta equals 3, which means the tangent of theta is equal to 1, which means that theta must be pi over 4 radians. So now our limits of integration are from 0 to pi over 4. The secant squareds cancel. The 9's cancel. We'll bring the 3 out in front, so we have 3 times the integral from 0 to pi over 4 of the tangent squared of theta d theta. Tangent squared on its own does not have a straightforward antiderivative, but we can rewrite it once again as secant squared theta minus 1. So we have 3 times the integral from 0 to pi over 4 of secant squared theta minus 1 d theta. We can antidifferentiate both of those easily, so we get 3 times the tangent of theta minus theta from 0 to pi over 4. We've already changed our limits, so no need to go back to x. So we get 3 times the tangent of pi over 4 minus pi over 4. And then from that, we will subtract the tangent of 0 minus 0. So we have 3 tan pi over 4 minus 3 pi over 4. The tangent of 0 is 0. And the tangent of pi over 4 is 1, so we end up with 3 minus 3 pi over 4 as our final answer. Let's take a moment to recap and summarize the 3 formulas we've just seen. So when our integrand contains the pattern a squared minus b squared x squared, we're going to replace bx with a over b sine theta. That's going to allow us to introduce an a squared cosine squared theta, which we can hopefully integrate more easily. If we have a squared plus b squared x squared, we'll use a tangent. So x will be equal to a over b tangent of theta, which is then going to turn our integrand into a squared secant squared theta. And then b squared x squared minus a squared, we'll use x equals a over b secant theta. And that's going to allow us to replace the pattern in our integrand with an a squared times the tangent squared of theta. Now that we have seen how to use these formulas, let's revisit the question that we started with. So you'll recall that we motivated this conversation by examining the length of the curve y equals x squared on the interval from 1 to 2. And we saw that that length was equal to the integral from 1 to 2 of the square root of 1 plus 4x squared dx. You can see that that integrand has that our pattern, one of our patterns sitting inside of it. This is a squared plus b squared x squared. And in that case, we have a is 1 and b is 2. So we see that x is going to equal a over b, 1 over 2, times the tangent of theta. That's going to give us that 2x is tangent of theta, which makes the 4x squared in our integrand equal to the tangent squared of theta. We also know by integrating this that dx is going to be 1/2 the secant squared of theta d theta. So we'll re-express our integral, our length, in terms of theta now. We're going to get the square root of 1 plus the tangent squared of theta. And then we have times 1/2 the secant squared of theta d theta. Let's investigate what happens when we try to switch our limits. If we do that, when we start off with x equals 1, that means that 1 is half the tangent of theta. Multiplying this out, we get 2 is equal to the tangent of theta, which makes theta equal to the inverse tangent of 2. That's not a particularly helpful number, so it might be best in this case to just leave things in terms of x and then evaluate at the end by switching back from theta to x. So that's how I'm going to proceed. You're not under any obligation to do it this way. You can, in fact, use inverse tangent of 2 and inverse tangent of 4 as your limits and do some different work at the end to evaluate. All right, so now this becomes the integral of the square root of 1 plus the tangent squared becomes the square root of secant squared theta using the Pythagorean identity. And then we have 1/2 secant squared. I'm going to go ahead and move that 1/2 out front. And I'm going to continue to note that my limits of integration still belong to the variable x. They're not the variable theta. All right, so now we can take that square root on the inside, and we now have the secant cubed of theta d theta. This is one of our higher powers of a trig function, so we may need to utilize a reduction formula in order to evaluate that. So let's recall that the integral of secant to the n of x dx is going to be equal to secant to the n minus 2 of x times the tangent of x all over n minus 1 plus n minus 2 over n minus 1 times the integral of secant to the n minus 2 of x dx, where n is equal to 1. In our particular case, we have an n value of 3. Using our reduction formula, we now get that our length is 1/2 times the quantity. We're going to have secant to the n minus 2, that's the first power of theta, tangent of theta, all over n minus 1 is 2, plus 1 over 2, times the integral of secant to the n minus 2, that's 1 again, secant of theta d theta, and we're evaluating that whole expression in terms of x from 1 to 2. All right, now we have to remember that the antiderivative of secant theta, you can get this by doing a multiplication by 1 of the form secant x plus tangent x over secant x plus tangent x. We've worked through that before, so I'm not going to do it all here, but we're going to get 1/2 the natural log of the absolute value of secant of theta plus tangent of theta. And we're evaluating all of this from x equals 1 to x equals 2. So now we need to figure out what secant of theta and tangent of theta are equal to, given that when x is 1 and x is 2. So we started off with the idea that x was 1/2 tangent of theta, which means that 2x is equal to tangent of theta. So we can replace all of our tangent x's with, or tangent of thetas with 2x. Secant of theta, we think about the triangle here. We know that if this is our theta, angle theta, we have a 2x and a 1 there to make the tangent of theta equal to 2x, opposite over adjacent, which makes this side of it 1 plus 4x squared, the actual integral we started with. And so that means that the secant of theta, secant is hypotenuse over adjacent. Secant of theta is in fact going to be 1 plus 4x squared, which is the integram we started with. All right, so using all of that, putting that all together, we're going to see that our length is now 1/2 times the quantity. Secant of theta is the square root of 1 plus 4x squared. Tangent of theta is 2x all over 2 plus 1/2 the natural log of the absolute value of the square root of 1 plus 4x squared plus 2x for tangent of theta. And we're evaluating. Now we're in terms of x, so we can just put a 1 and a 2 there. Our variables all match up. We'll plug in. So we'll plug in what we get when we plug in 2 first. So 1 plus 4x squared when x is equal to 2 is 17. So we get the square root of 17 times 4 over 2 plus 1/2 the natural log of the absolute value of the square root of 17 plus 4. Then we're going to subtract the terms when we plug in 1, so we get minus, plugging in 1 for x, we get the square root of 5 times 2 over 2 plus 1/2 the natural log of the absolute value of the square root of 5 plus 2. We can tidy this up a lot. We have 1/2. I'll leave that on the outside for now. I have these two cancel. So I have 2 square roots of 17. And then these two cancel. So I have minus the square root of 5. That comes from combining this term here with this term over here. And then I can use my properties of logarithms to combine these two terms, right? I have two logarithms separated by a subtraction. This should have been a negative sign because I was subtracting off both terms when I plug in one. So, little sign error there, but we fixed it. So now we have two natural logs separated by a subtraction, which means we can convert them or combine them using division. So we get 1/2 the natural log of, I don't need the absolute values because all of the expressions inside of them are positive. So I get the square root of 17 plus 4 all over the square root of 5 plus 2. And then we can, if we so choose, we can distribute the 1/2 to get the square root of 17 minus the square root of 5 over 2 plus 1/4 the natural log of the square root of 17 plus 4 over the square root of 5 plus 2. Now, we have to remember that our original task was actually to find the length of a curve. This might not be a particularly useful answer, so we can plug that into our calculator and see that that is approximately equal to 3.168 units of length.